Hello, class. So today I'm going to help you solve problems that have to do with energy. So let's look at this first problem here. So in this problem, the problem says that no thermal energy was generated. So in this situation, we only have kinetic energy and potential energy. There's no thermal energy that's being generated by friction. So the question says, calculate the cart's potential energy and kinetic energy at each of these points, point A, point B, and point C. So we have to find its potential and kinetic energy at each of these points. Okay, so let's start by finding the potential energy of the cart at point A. So potential energy equals m for mass times g for the acceleration due to gravity, which is always just 9.8, times h. So the mass of the roller coaster is 1,000 kilograms. Kilograms always means mass. It's the unit of mass. So here I can write 1,000. And g is always just 9.8. And h is height. So the height of this ball is 100 meters. So if I multiply those three numbers, so 1,000 times 9.8 times 100, I get 980,000. So the potential energy of the cart is 980,000 joules. So right here, I am going to write 980,000 for the cart's potential energy at point A. And what is the cart's kinetic energy? What is the cart's kinetic energy at point A? Well, the cart has a velocity of 0 meters per second. And so because its velocity is 0, the cart's potential energy at point A is 0 joules. Okay, so let's find the cart's potential energy at point B. So at point B, its potential energy equals mass, which is still 1,000, times g, which is always 9.8, times its height, which is 80 meters here. And so that equals, so 1,000 times 9.8 times 80 equals 784,000. So its potential energy at this point, point B, is 784,000. All right, so what is its kinetic energy at point B? What is its kinetic energy? So the very important thing about energy is that the total energy of a system always stays the same. The total energy of the system always stays the same. So what that means is that these two numbers added together always stay the same at each point throughout the object's journey. So 980,000 plus 0 equals 980,000. And so these two numbers added together have to equal 980,000. And these two numbers added together have to equal 980,000. So, to find the cart's kinetic energy, I have to subtract 980,000 minus 784,000. So 980,000 minus 784,000 equals 196,000. All right, so we're almost finished with the problem. So here at point C, the potential energy of the cart is, again, the potential energy at point C is the mass, which is still 1,000, times G, which is still 9.8. But now the height of the cart is 0 meters. So times 0. And so that multiplied together equals 0. So the potential energy of the cart is 0 joules here. So the unit of energy is joules, which is what I'm writing for all of the energies. And the kinetic energy of the cart then, because these two numbers have to add up to be 980,000, so the kinetic energy of the cart has to be 980,000. All right, class, so now let's look at this question. A skateboarder drops into the course below. Rank the speed of the skateboarder at each point, assuming there is no friction on the track. At which points is the speed of the skateboarder equal? So a skateboarder is dropping into this course, and the question is asking us to rank the speed of the skateboarder at each point along the course. So when is the skateboarder going the fastest? And when is the skateboarder going the slowest? And when is the speed of the skateboarder equal? So let's rank the speed of the skateboarder from slowest to fastest. So if you're a skateboarder and you are going down this track, your speed, what will happen to your speed when you drop from the top of the hill to the bottom of the hill? Will your speed increase or will it decrease? So your speed increases. When you move down a hill, your speed increases. And when the skateboarder goes back up the hill, the speed decreases. Okay, so what that means is that the higher up you are on this hill, the higher up you are, the slower your speed. And the lower you are on this hill, the faster your speed. Okay, so to rank the speed of the skateboarder from slowest to fastest, you just look, where is the speed the highest and where is it the lowest? And where it's the highest, the speed is the slowest, and where it's the lowest, the speed is the fastest. So let's look. So the skateboarder is the highest at point A. So they are moving the slowest at point A. The next highest is point D. So they are moving the next slowest at point D. The next highest are points B and C. So they are moving the next slowest at points B and C. And the lowest point is point E. So the skateboarder is moving the fastest at point E. But at which points is the speed of the skateboarder equal? So at the same height, the skateboarder will have the same speed. So at points B and C, the skateboarder will have the same speed at those points. All right, class, so now let's look at this problem. What height would you have to drop a 100 kilogram roller coaster from in order for its speed to be 5 meters per second at the bottom? How about a 50 kilogram roller coaster? Assume there is no thermal energy generated by the roller coaster, so no friction. Okay, so we have a slope and we have a roller coaster that is going down the slope. And we want to know what height do we have to drop the roller coaster from in order for its speed to be 5 meters per second at the bottom of the slope. So let's think about this situation in terms of the potential energy and the kinetic energy, again, of the roller coaster. So at this point, at the top of the slope, the roller coaster has a speed of 0 meters per second. We're going to drop it from rest. And so what would the potential energy be, what would the kinetic energy be of the roller coaster at this point? What is the kinetic energy of the roller coaster at that point? So because the roller coaster is at rest, its kinetic energy is 0. And what is the potential energy of the roller coaster at that point? So at that point, let's call this point A. Okay, so at point A, the potential energy of the roller coaster is mgh. So it's mass times 9.8 times height. So the potential energy at point A is the mass of the roller coaster. The mass of the roller coaster is 100 kilograms because kilograms always goes with mass. So 100 times G is always 9.8. So 9.8 times the height. So the height is what we are looking for. So I'm just going to write H. And so the potential energy of the cart at point A is 100 times 9.8, which is 980 H. So I'm going to write, again, 980, right there, 980 H. Okay, so now let's look at point B. So let's make this point B at the bottom of the slope. So at point B, now at the bottom of the slope, the height of the roller coaster is 0 meters. Its height is 0 at the bottom. So the potential energy of the cart at point B is m times g times h. And so it's, again, 100 times 9.8, but now the height is 0. The height at the bottom of the slope is 0. So the potential energy of the cart at the bottom of the slope, point B, is 0. So I'm going to write 0 right there. And the kinetic energy of the cart at point B has to be, the speed of the cart has to be 5 meters per second. So the kinetic energy of the cart at point B, so the kinetic energy is given by the equation 1/2 mv squared. So because the velocity of the cart at point B has to be 5 meters per second, we can put 5 in for the velocity of the cart. And we know its mass is still 100 kilograms, so we can put 100 in for the mass of the cart. So the kinetic energy of the cart is 1/2 times 100 times 5 squared. And so if you do that calculation, you get 1,250. So the kinetic energy of the cart at point B is 1,250 joules. Okay, so how do we find the height of the cart, which is what we are looking for? So we find the height of the cart because, remember, the most important thing we learned in this unit is energy is always conserved. So the potential energy and the kinetic energy added together, the total energy of this cart, the total energy of the cart always stays the same. And the cart's potential energy at the top of the ramp is just changing into its kinetic energy at the bottom. The energy of the cart being high up is changing into the energy of its movement when it gets to the bottom of the ramp. And the total energy always stays the same. So what that means is that the potential energy here plus the kinetic energy here at point A equals the potential energy plus the kinetic energy at point B. So that means that the potential energy plus the kinetic energy at point A equals the potential energy plus the kinetic energy at point B. So that means that 980 H plus 0 equals 1200 equals plus 0 equals 1250 plus 0. And therefore 980 H equals 1250. And so if I divide both sides by, if I divide both sides by 980, then I get H equals 0.26 meters. So this height is 0.26 meters. All right, class, so now let's look at this problem. So this problem says a ball is dropped from the ramps below. It is dropped from the same height on both ramps. Which ball will have a faster speed at the bottom? And why? Explain your answer. Okay, so these balls are being dropped from the same height. And so that means that their potential energy is equal to each other because they are at the same height. And so at the bottom of these ramps, if all of the energy was conserved, that means if all of the potential energy, was converted into kinetic energy, so that is the speed of the ball. If all the potential energy from the height is converted into the speed of the ball at the bottom of the ramp, then the speeds of these balls would be equal. So if all of the energy was converted, the speeds would be equal. So that is why if you have two curved ramps and you drop a ball from the same height of the curved ramps, at the bottom of those ramps, the speeds of the ball are equal. If the ramps are curved. So only if the ramps are curved. And why is that? It's because in these ramps, no energy is being lost. So all the energy from the ball's height is converting into its speed. And so since the ball has the same height, no matter the shape of the curve, the ball will have the same speed at the bottom of the ramps. So the only difference, though, here with this ramp is that not all the height is turning into the speed, because some energy is lost on this ramp. And why do you think energy is being lost when the ball goes down this ramp? It's because when the ball hits this part of the table, it bounces a little bit. And so when it bounces, it loses energy. And so because of that, because this ball loses energy when it bounces, that is why it is converting less potential energy into kinetic energy, because some energy is being lost when it bounces. And so it's converting less of its height into its kinetic energy. So its speed at the bottom would be less. So this ball, it moves slower at the bottom of the ramp because it bounces. Because it bounces. And if it did not bounce, so if there was no bounce, it would have the same speed.